can also see in Claudia's group if like Walker and Power are going or something. Because also there's a pot of money with the CSC for music. Where money goes. Interesting. It's a bit complicated.
Hi again, everyone. So I just want to pick up where I left off yesterday. I was talking about deformations of a theory that's written in DG formalism, maybe a topological theory, and how they're classified. And the last thing I said was that there's this more Cartan equation around. And I want to say a little bit more about that. So the setup is that we have a field theory where we're imposing topological invariance on local operators in a cohomological way, assuming local operators are Q cohomology of all operators one might write down, where in BV Q is declared to give us the equations of motion. The part where topological comes in is assuming that the equations of motion actually make things locally constant. So it's like assuming a precise form for the equations of motion so that space-time can be stretched. And in that sort of setting, descendants exist. So when for all local operators, there are descendants that impose topological invariance cohomologically. They essentially say, they give you in a fancy homotopy way, they give you the homotopy between inserting local operators at two different points and not. So the last thing I said yesterday was that deformations of such a theory in one dimension, there's a straightforward generalization to any dimensions. Are classified by local operators. Mu such that mu is odd. It has cohomological degree 1. And it satisfies the more Cartan equation. And how does that work? The actual deformation changes the action by the integrated first descendant. And the place where the more Cartan equation comes in is in checking that this is a Q-closed variation. So naively, you would just go in and hit this with Q, get get a total derivative and say, okay, if there are no boundary terms, you're done. But it's not enough to check that that Q of the variation is closed. In order to be able to insert this thing into correlation functions, the insertion is actually the exponential of this, and it's a path-ordered regularized exponential of that. So what you actually need is that Q what's it about it? It's a path-ordered exponential of this thing. Is 0. That's what's actually deforming correlation functions, with the additional assumption that you somehow regularize so that you don't hit local operators that are around. And the place where the Moore-Cartan equation comes in is just in expanding this out. So it's got a constant term that Q doesn't care about. And then a linear term. And then a quadratic term, which, if I pay attention to the path ordering, looks like, let's see, 1. And then further integrals along simplices.
Also the factors from the exponential, right? Like 1/2 for the second integral, and also the factors from the exponential, right? Like 1/2.
Yeah. So I've.
Or is that okay? Yeah.
So I can write it as a half times an integral where t1 is not equal to t2, where I've removed the diagonal, or reabsorb them and just write them as integrals over simplices.
I see. Thanks.
And right, and then we use the descent equation. So that's minus. Well, so first there's a total derivative around. So that's d of mu, which, assuming there's no boundary here, boundaries will affect the action of mu on local operators, which is not what I'm checking right now. So the total derivative goes away, but there's the second term in the descent equation. Q mu first descendant. And then I look at this quadratic term, which now has an interesting total derivative because this has an interesting boundary. And if you are careful about signs, this should look something like T of mu, T2, mu1 of T1, mu1 of T2, mu at T1, plus other stuff. And so there's another term of the form Q of the quadratic thing descended. And then there's the cubic stuff, and then the entire series. This total derivative has a non-trivial boundary contribution from removing the diagonal. So the boundary contribution is an integral along one copy of R, and it needs to somehow cancel with this integral along one copy of R. And so the thing that these two together end up giving you is minus Q mu. It's minus integral over R of Q mu1 plus mu. Great. And then the different times that keeping track of the ordering of times tells you that if you treat this as an operator equation, you get the mu's in different orders and end up with something like the commutator of the descendant of mu and mu itself. Plus other stuff. And this thing is the first descendant of the Mohr-Cartan equation. So this vanishes, this vanishes. And then you need to worry about the higher order stuff, but everything will keep, the effect propagates, and everything will keep vanishing in pairs all the way down. Okay, so that's where that comes from. And then if this was at all fun, then you have an exercise to do. To check that the effect of the deformation on local operators is to change the differential. So initially, initially we had some action of this thing called Q, which was a symmetry. And after turning on this variation of the action, we just get an extra commutator with A, commutator with mu. Also, on the Hilbert space, or the vector space of states, initially, abstractly, quantum mechanics in this cohomological setting looks like a vector space with a differential. And its algebra of operators is endomorphisms of a vector space with a differential, which is an algebra with a differential. And on the vector space of states, the differential is just add mu to it. And in this, so there are two things to say. The easy thing is, if you believe this, then it's very easy to figure out where the Mohr-Cartan equation comes from. It's just the condition that the new differential Q plus mu squares to 0. That would have been a more direct way to go about it. But I find it enlightening to tie into the continuum field theory formulation. And so the last part of that, which is your actual exercise, is to figure out why correlation functions how to say this? So y expectation values of operators after the deformation look like sorry, am I being gonged out? Looked like deformed differentials applied to expectation values before the deformation. That's the main difference, and I think that's the way I want to write it. Sorry, that's not the way I want to write it. I'm going to probably put a Q on the outside. Where what is this? This is the thing where you integrate mu1 from all around the operator. There are little boundary terms that pop up, and you can connect with the more abstract algebra formulation. Okay. Someone yesterday very wisely asked for some examples of deformations. And there are some nice things to say about them. So I'll give you two. We take quantum mechanics, topological quantum mechanics with essentially a boson and a fermion. So the operator algebra looks like it contains two bosonic generators and two fermionic generators. Everything commutes up to signs, and the commutation relations are the canonical ones. There's no particular, I'm not actually thinking of complex conjugation in writing X bar. You could have written P instead. The relations look like that. There is a setting in which this naturally arises as a twist of some theory where X bar is actually the conjugate of X. And in BE, everything gets promoted to forms. So the BV fields. Oh, sorry, I should tell you what the vector space is as well. So it's a little tricky for the bosons. There are multiple ways to quantize the space. If you're happy doing this algebraically and not worrying about Hilbert spaces, you can take the vector space to just be functions of X and psi. It's some sort of functions of X. Here I'm just taking polynomials in which X bar X is a derivative. The BV fields involve not just X, but descendants. Blackboard bold X. So that's a multiform on R. And just to emphasize, the descendants have opposite statistics from the original field. So X1 is something like x1 t component dt, where if x is even, the component of x1 is odd. And the psi is exactly the same thing, and so the action ends up looking like x dx plus psi d psi, where I've turned everything into multiforms by adding a descendant. So to here you can add. So the easy way to say it is that you could add any polynomial in the x's and the psi's as an interaction, but it needs, so this corresponds, if I do this in these sort of multiform superfields, I don't actually need to keep track of taking descendants. This corresponds to just an ordinary Moore-Cartan element, mu, without blackboard bold. Not all of these satisfy the Moore-Cartan equation. The thing needs to square to 0. So q, in this simple example, q just acts as 0 on, like I started with an algebra that didn't know about q at all. Q just acts as 0 on x and psi and x bar and psi bar, but there's a non-trivial constraint that this squares to 0. So an example of the thing that satisfies that is just x psi, which is adding a mass term to this quantum mechanics. So the variation of the action is like that. I maybe need a show of hands, so I might make some comments about like twisted quantum mechanics. If I say the words like the B twist of n equals 2 quantum mechanics and ENJ superpotentials, is that language familiar to anyone here and at all helpful? Awesome. Okay. So this is a quadratic mass term that trivializes the entire theory. It adds, so first it squares to 0 kind of trivially because there are no x bars and no psi bars. So there's nothing to worry about in the commutation relations. And it adds the easiest way to see that it trivializes the theory is that it adds a differential to V. Whose cohomology is trivial. If we think of V as functions of x plus functions of x times psi, that differential just goes from functions of x times psi to functions of x and multiplies by x. And so its kernel is, sorry, it goes the other way. It's from functions of x to functions of x times psi. Its kernel is anything that has a psi in it. It's the second component. Its image is everything in the second component that doesn't have an x. And kernel mod image is just the linear space, the one-dimensional space span, right?
Commutators rather than anti-commutators because you have in mind the twist?
No, they're all anti-commutators. I'm just writing them the same way. With the assumption that whenever something is odd, you should read it as an anti-commutator.
I have a stupid question. Are you assuming that Q acts trivially on all X bar CMC bar?
I was, yeah. So, so I should have been more careful. So Q acts on all the superfields in all these multiforms. Q acts as the exterior derivative. Before I said anything about continuum theory, I know what the physical operators are. They're x and x bar and psi bar. And so these had better be in Q cohomology, and Q had better act as 0 on them. And then I reconstructed some theory in which that was true. So yeah, Q had better act as 0, and it does. So in fact, Q acts as D on anything. On any superfield. Which implies that on the 0 form components, it acts as 0. And on the 1 form components, it acts as D of the 0 form components, which is the descent equation.
I'm confused about this action on V, this multiplication by psi, no? In the last line, V CFX plus CFX psi. If you take an element in the first CX, you will have to multiply by psi, or?
Yeah, so I multiply by, it's just, yeah, so it's multiplication by this.
Then the arrow?
Right, so
Sorry if this is a stupid question.
The arrow is the multiplication by psi, and the little x on the arrow is multiplication by x.
Okay.
Sorry, that what was in my mind was not matching what was in your mind. Okay. Maybe a more fun example, gauging a Lie algebra symmetry.
Another stupid question. The product of the multifields is just wedging the two forms. The product of the multifield is just wedging the forms.
Yes.
Okay.
Yeah, there are wedges everywhere.
Okay. Good. Thank you.
Yes. So suppose we have quantum mechanics with the G symmetry. That means it's got currents. So we have a Lie algebra with some basis. And structure constants. Then and that Lie algebra acts on some quantum mechanics, that quantum mechanics should have local operators that represent the algebra. So the J's obey the same relations. and their physical operators. Q is going to act as 0. How do we gauge this? We'll tensor with 1D gauge theory. Which has in it one of these multiform fields that has a leading 0-form component, that's the ghost, and a 1-form component, that's the connection. So broken down, the ghost is odd, and the components of the connection are even. They have opposite parity, as they should. So A is the first descendant of the ghost. In components, C is like C with little a times the basis of the Lie algebra. The way Q acts is that on the gauge sector, that Q of C, it's the BRST action or the Chevalier-Eilenberg action is minus a half F BCA CBCC. Given that, so far these are theories that don't talk to each other. Gauging is coupling them together. So there's a more Cartan element for the gauging. That's J times C. In other words, you deform the action by J times the first descendant of C, which is the connection, which is how you gauge. And then you go and check that the more Cartan equation is satisfied, which is not trivial. It involves the fact that the commutators of the J's involving the structure constants match the differential of the C's involving the structure constants, perfectly dual to each other. And then the other thing you need to check is that the new, after you've gauged, the new differential, the Q plus mu differential, in the product theory, what does it do? It's the old Q plus CAJA, this mix thing, which says, what does commutator with JA do? It's what used to be a global transformation in the original quantum mechanics, because the current, in 1D it's just the charge, generates gauge transformations, but now those gauge transformations are coming with a coefficient, that's the ghost, which is the correct BRST gauge transformation. And cohomology of this is precisely the projection to gauge invariance in the continuous case. And this whole thing is called Chevalier-Eilenberg cohomology, but just the way it shows up in physics. And a really nice thing is that this sort of procedure generalizes to higher dimensions. There one place where it was made precise and explicit was a paper about 1.5 years ago of Gayoto, Kalp, and Wu. So they weren't talking about a topological case. Well, they were interested in holomorphic theories, but they said some things that worked in general. And one upshot is that if you try to gauge Lie algebra symmetries in BE formalism, and maybe, sorry, what I'm about to say is much older and well known in BV formalism. I think the way maybe they formulated it in this paper connects more directly with the way some family of physicists might like to think about what's going on. What I want to say is that, so right, when you gauge symmetries in BV, this corresponds to a deformation. And deformations in any dimension are classified by an appropriate version of a Moore-Cartan equation. And it's a Moore-Cartan equation for L-infinity algebras. But it's extremely explicit, just as explicit as the board that is maybe still here. Nope, it's the one I just erased, that involves some sort of regularization procedure for having, you have some exponential and you de-exponentiate it and you need to point split or do something to regularize and you get boundary terms. And figure out what you need to get Q of an Rn of some deformation, an interaction term, to be 0. There are ways in which this can fail, and the ways in which this can fail are the standard perturbative gauge anomalies. In physics terms. In QFT, there's a potential anomaly to gauging that that involves trace of f. And in 4D, there's an anomaly that involves trace of f squared, and so on, and that shows up out of this. I'm saying this to say, like, it's different formalism to describe something well known, but it's different formalism that might be quite useful if one wants to carefully keep track of what's going on, and possibly if one's trying to figure out how to deal with continuous symmetries. There may be other papers to state in this context. There's work of Brian Williams and collaborators involving gauge anomalies and ANC anomalies in 4D superconformal theories and related work of Bowman and where the idea is all the same. All of these anomalies somehow get repackaged in solutions to some appropriate Moore-Cartan equation, and higher operations involving descendants. Okay. Let me then move on to categories. So. Yeah. So I talked a lot about quantum mechanics, and I focused on the topological case of quantum mechanics, and the reason for that is because I actually care about categories of line operators in higher dimensions. A line operator sitting inside, say, some d-dimensional QFT is a lot like quantum mechanics. The main difference, this thing O, the main difference is that there's no state space. It does, however, have, there's no state spaces because there isn't some isolated one-dimensional system here. It's sitting in a bath of d-dimensional QFT. There are ways to create state spaces by maybe choosing a vacuum at infinity, or like compactifying space, or evaluating it, well, putting boundary conditions in, doing something like that. There are ways to pull vector spaces out of this. All of these options give you fiber functors of various kinds on this category, which I'll probably talk about after the break. There's no canonical way to do that. Intrinsically, lines don't carry vector spaces. They do, however, have algebras of operators. And the algebras of operators work almost the same way as they do in quantum mechanics. The main difference in operators is that they can get singularities of the same kind that exist in higher dimensional QFT. So I would say abstractly that a line operator or a defect in higher dimensional QFT is a collection of operators that can be put on this defect that have mixed correlation functions with operators in the bulk. But precisely because they can interact with operators in the bulk, there can be bad singularities. In quantum mechanics, there are no singularities. Operators along the line can be collided with each other in a singularity-free way. If you move them past each other, there might be a step function jump, which is where commutators come from in the algebra. In quantum mechanics, that's as bad as it gets. There's no renormalization or fancy regularization procedures that one needs to implement. And in higher dimensions, there are, and things get weird. Nevertheless, there's some. When I say there's some algebra, I actually, in saying that, I mean algebra in the same way that I mean algebra of operators in the bulk of a higher dimensional theory, which is some funky factorization algebra sort of thing. If the quantum mechanics is topological, or rather, if there's no quantum mechanics, if the direction parallel to the line has some topological invariance, then A is an actual algebra. It's got a product. From collision. And because of topological invariance, it doesn't matter how far apart you put these things. But if you're in a continuum theory that requires you to somehow regularize what you mean by equations of motion and funny boundary terms and work, for example, in DV formalism or in some cohomological setting, then topological invariance doesn't hold on the nose, it holds in cohomology. The precise statement is that it's an infinity algebra. In 1D quantum mechanics, A was a DG algebra. All it has is a product and a differential. So it has M1 from A to A given by the differential, and it has M2 from A squared to A given by the product. But in higher dimensions, even higher ambient dimensions, the sort of singularities that can happen in general QFT in higher dimensions end up messing this up. And we get higher associativity relations that are encoded in higher products in an A-infinity algebra. So you don't need to know much, and I don't want to spend a huge amount of time talking about this because I think I'm not going to have time to really use it in a really good way in later lectures. So let me just say quick things about it. So one of the points of the higher operations is to tell you exactly how, like M3 tells you how the associator for the multiplication might not be 0 on the nose, but might be Q of something. And what it's Q of is M3. And then there are higher associators that are Q of the higher M's. All of the physical definition of all of these is extremely explicit if you're in a perturbative setting and have descendants around. So I've told you what the product is. M3 is for a line in some ambient space is put three things on the line, but take the first descendant of the middle one and integrate it between the top and the bottom. And then it's very easy to check that Q of this by the descent equation is actually the associator. You get boundary terms, and you get AB up here as one boundary term, and C far away, and BC down here, and A far away as the other boundary term. And all of the higher m's are defined the same way. They're integrals of descendants of the middle things integrated between the top and bottom. If I do this in quantum mechanics, nothing interesting happens. What happens in higher dimensional field theory is that all of these interact with the bulk. And if you're actually, say, computing them perturbatively, there are Feynman diagrams involving bulk local operators that correct this and go into the computation of the correlation function that actually defines the higher multiplications. That's sort of why these are generically non-trivial in higher dimensions. These are not just a function of perturbation theory or a feature of perturbation theory, and any sort of QFT, no matter how you define it, should have a structure like this. If you want a very different definition, you can take a look at Gayoto-Moore-Witten. Who defined the same sort of structure using solitons in a massive topological theory in the infrared. The structure should be there. Exactly how you define it depends on how you describe your QFT. The thing I want to do for the rest of these lectures is to represent lines in higher dimensions. I should say lines form a category. And the reason they form a category C, whose objects are the labels of the line operators themselves. They're the distinct sets of collections of algebras of operators that I can put on the lines that interact with the bulk. And the morphism spaces are the vector spaces of local operators at junctions. Which one could describe as bimodules for the two algebras on the other side, on the either side, on either side. Altogether, the Hom spaces between collections of objects have the structure of an A infinity algebroid, and you get compositions, but they're compositions up to homotopy. And so this thing in general is an A infinity category. Yeah. I want to take a break very soon, and so I'll say one more thing about what sort of category this is. So I think the most general thing you should always have in mind is that you're shooting for an A infinity category. Sometimes this simplifies, and sometimes you can simplify it yourself. The sorts of things I have in mind. If you have a particularly nice model for your quantum field theory, you may find a DG model for the category C. So what I mean by that is that in the world of A infinity algebras, in some formal mathematical sense, every A infinity algebra is isomorphic to a DG algebra, typically a really, really big one. The physical intuition behind that is RG flow. Theories with a lot of really complicated interactions might flow from theories in the UV with some very, very simple interactions in the bulk. And so sometimes you can find a UV theory with very, very simple interactions that makes sure that these higher operations are all zero. And so you get a model that maybe has a lot more fields, because in the UV you have a lot more fields, but has very simple operations. Schematically, find an A tilde that is isomorphic to A, but is much bigger, but the M the higher M's vanish. Whereas if you, in physics words, integrate out a bunch of stuff, or in math words, take cohomology or some partial cohomology or manifest this isomorphism, to actually get an isomorphism, you need to correct with a bunch of higher operations on this side. So that's a thing that can happen. The other thing to say is that the word derived category comes about frequently. Derived categories are typically things that live in the DG world. So they're derived categories of an abelian thing, and with some work, one puts a DG structure on them. The thing I wanted to connect with was semi-simple things. So a particular example is a semi-simple category. Which sort of is, it's a DG category and it's an A infinity category where all the extra A infinity fluff is trivial. There is Let's see for the other example. And there are better ways to make that precise, but in saying that I'm working with the infinity categories, I'm not ruling out the fact that things that maybe a lot of you guys care about are actually just embedded in here. This is just a more general study. Take a break, and thanks.